Welcome to Inside Bioprocessing, a Thermo Fisher scientific podcast discussing key trends and topics within the bioprocessing industry. In this episode, we will be talking about continuous perfusion bioprocessing and its potential to enhance biopharmaceutical production. Since its development in the 1980s, perfusion cell culture has been used for the manufacture of toxic or unstable proteins, such as haemophilic factors. More recently, however, innovations in automation, cell lines, and single-use technology has made this method more accessible to the wider biopharmaceutical industry. As a result, there has been significant growth in the use of continuous perfusion for the production of less specialized molecules due to its ability to reduce costs, increase productivity, and improve protein quality compared to traditional batch and fed batch methods. To discuss the current state of continuous perfusion, as well as its future, we are joined today by three experts currently working in the perfusion field. Please join me in welcoming Vicky Goralczyk, Director of Cell Line and Bioprocess Development at Fioni Bio, Ji-Hong Guo, Head of the Cell Process Development Department at Mycinax, and Christopher Brow, Research and Development Staff Scientist and Engineer at Thermo Fisher. Ji-Hong, could you give a brief overview of continuous perfusion and how it differs from traditional bioprocessing approaches such as batch and fed batch processes?
Continuous perfusion is carried out by constantly feeding fresh medium into the culture, while also constantly removing spent medium with cellular waste out of a bioreactor at the same flow rate. During the culture period, most of the cells are kept in the reactor with a cell retention device. Unlike batch and fed batch cultures, where cellular waste accumulation inhibits cell growth, this continuous medium exchange allows for the support of cell densities that can be 3 to 5 times higher without sacrificing viability, often for longer periods of time, compared to a period of 10 to 18 days for batch and fed batch culture. The duration of continuous perfusion can be extended all the way to 90 days. In addition, products of batch or fed batch culture can only be obtained at the end of the process, whereas perfusion culture, the product can be continuously exported and harvested earlier.
So now we know a bit about the traditional bioprocessing approaches. Can you explain how continuous perfusion differs from other types of perfusion processes?
There are three other types of processes which also utilize perfusion for distinct applications, but they operate a little differently. The first process is N-1 perfusion, which is designed to achieve very high cell density in the log phase within 4 to 7 days to inoculate the bioreactor at high initial cell density. Since high cell numbers is a major goal and the productivity is not taken into account, I think media supply can be significantly more than cell demand, and bleed is not necessary. The second is concentrated fed batch, which is ideal for a stable protein with low productivity. The cell density is also enhanced by perfusion, but both the cells and the products are continuously kept in the reactor to accumulate large amounts of the product by the end of the culture. As such, a cell retention device with filter pore size smaller than the product is needed. This process duration is about 14 to 20 days because no cells are removed from the system. The third is intensified fed batch, which is often adopted to produce an ample amount of lay bioprotein within a short period. Unlike concentrated fed batch, the product is moved from the reactor continuously. The medium exchange rate needs to be optimized to lower the production cost, which often makes the process very efficient. Without cell bleed, the process can last around 16 to 25 days. The purposes of the three processes are to harvest sufficient product amounts within the short period. Thus, cell bleed and the steady state culture are not necessary, which is the biggest difference compared to the continuous perfusion.
And finally, Ji-Hong, what would you say are the essential elements of a successful continuous perfusion workflow in terms of equipment, media, cell clones, things like that?
To me, the upstream process consists of three elements: the cell line, the medium, and the parameter control. A cell clone suitable for perfusion cultures should be a high QP or cell-specific productivity clone. Because perfusion significantly increases the cell density, the high QP multiplied by large numbers of cells creates much more product daily. Furthermore, long-term production stability is also important for the clone because perfusion culture can be extended to 3 months. Lastly, high cell density means much higher oxygen demand, which can only be supported by high agitation speeds and gas flow rates. As a result, tolerance to the mechanism shear force is also necessary for the selected cell clone. Uh, In terms of the medium for continuous perfusion, there are distinguishable difference from batch and fed batch processes. To support a higher cell density, the nutrition concentration should be enhanced while ensuring a stable osmolarity as well as balance among various substrates and metabolites. When considering the cost of goods, the perfusion medium exchanging rate or perfusion rate has to be optimized in order to greatly decrease the medium usage during the perfusion process, reducing medium costs and storage space. Most important, this lessens the burden of the cell retention device and smooths out the downstream process. The liquid handling is another issue in large-scale production. The amount of the media used in the perfusion process is significantly much more than that of a fed batch process. So I think perfusion medium must be prepared with as little of footprint as possible. The last element is parameter control. Continuous perfusion supports high VCD in a defined volume, where a medium keeps flowing in and the waste keeps flowing out of the system, creating a dynamic culture control condition. Various parameters like pH, pump speed, gassing, CO2 level, membrane or field clogging may negatively affect cell growth rate, titer, or quality. Hence, reliable equipment and a real-time monitoring system are always required. I recommend an integrated hardware and software system, particularly designed for perfusion culture, which could effectively decrease the possible risk from errors caused by equipment or manual operation during the long-term perfusion culture period.
Thank you for that overview, Jihong. So, Vicky, obviously, as Jihong mentioned, there's a lot of differences between batch and fed batch processes compared to continuous perfusion processes, one of which is managing incoming and outgoing materials. So, how important is it to manage liquid transfer when running perfusion processes?
You will generate a lot of supernatant harvest when you're doing a perfusion process. So you might need some more storage capacity in your facilities. Or you will need a DSP, which is high functioning and can work with all the supernatant which is coming through the system. Johan, would you add something here?
For the liquid delivery device, I think 3 individual tanks should be used in addition to corresponding pumps for liquid transfer. One for storage of fresh medium, one for spent medium, and the last for removed cells. If the liquid delivery device is not integrated into the bioreactor control system, I think the error arising from equipment and the manual operation can lead to difficulties in maintaining the perfusion rate.
So what we see from R&D, you're right, Jihong. We are using bottles to feed the bioreactor and another bottle to harvest the supernatant. And as these these liquids have to be pumped, you will need some pumps and you will need long tubings. That's also interesting, I think, at least for R&D. And what we've seen in GMP, when you get through the process through the GMP facilities, you might need some large tubings and long tubings to get the supernatant and the harvest to a cold room, for example, where you can store the supernatant until it goes through DSP then after that.
The preparation for perfusion process is more difficult and more complex because we have to prepare some tank for supernatant storage, and we have to make sure the pump can work precisely to maintain the perfusion rate at a constant rate. So I think it's the challenge. It's a challenge for the manufacturing plant.
So, Christopher, is there anything you'd like to add to this point?
I would say particularly when you're trying to maximize your productivity, the closer you run your process to the limits of nutrient utilization and waste removal, the more important that accuracy becomes to maintain. Just in very simple terms, if you're running close to the limits of a critical nutrient, you have to ensure the accuracy of your fresh media coming in is maintained. Otherwise, it could dip below that threshold and you could potentially lose your steady state, for example, if you're trying to maintain a continuous culture.
Yeah, so the logistics might be a big hurdle here. So we have run a GMP process with 1,000 liter working volume and 2 volume per day media exchange, so perfusion rate of 2. And I believe it was quite interesting. The medium was sold as liquid. So every day there was liquid coming in. And then every day they sent out the containers for the liquid back to the company who was then filling it again with fresh medium. So this was a logistic challenge, a big one, I believe. On the other hand, you can have a big storage room where you have all your 30,000 liters of medium or whatever you need. Or you can also just liquefy the medium yourself. So then you have to buy the powder medium and liquefy it.
If we now move on to actually implementing the perfusion process, Vicky, are there any particularly important considerations that biopharmaceutical manufacturers should be aware of before trialing continuous perfusion?
Yeah, so the first one, cell line requirements, I think it's quite important because we've seen that a cell line which is very capable in a fed batch process might not be that high producing in a perfusion process. So when we're looking into clone development, we're already screening for clones which have either better traits for perfusion processes or for fed batch processes. I don't think it's that easy to have a cell working in a fed batch process moving to a perfusion process. Then, yeah, screening times. That's also interesting, and that's also important. When you're doing a perfusion process and you know you want to have this process in a GMP run for 3 months or so, this means you will have a stability study which has to be done over 3 months at least, and you have to take into consideration the uprising of cells. If you need a lot of cells, and this might also take 3 to 4 weeks beforehand, and all the work on the cell clone which has to be done before has to be done on over all this lengths of time. So it's not you cannot do a perfusion process for only 2 weeks and then say this is a process I want to do in GMP for 3 months. We have been struggling with that because we wanted to have done a lot of experiments on one particular project, and what we decided to do was we looked into different conditions for the perfusion process during a 3 months long process where we changed the conditions every other week. So this might be an idea what you want to do, but from a scientific perspective, it's always better to have the process run with one condition from beginning to end. But this means that you have 3 months for each process, for each experiment you run. This takes a long time.
Well, I would say that's for that complete validation, right? If you're trying to assess an early assessment, even for a continuous process, it's reaching a steady state and confirming that steady state If you can achieve that, that at least lets you do some screening without immediately jumping all the way to 3 months.
So, can you use modeling to facilitate this validation process?
Yeah, having a scale down model that you trust is super critical. I've encountered quite a few situations where people were screening doing a flask, and your flask behavior in a simple batch rarely will give a very clear indicator of what you're going to get during perfusion performance, because the environment is so different, and the waste accumulation and nutrient balance that you maintain in a perfusion environment is very, very different from what you'll encounter in a flask. So yeah, I think you can't overstate how important it is to have a screening model that you have verified translates to your actual perfusion operating environment. And even then, I think your upfront work, to Gian's point, is going to be a little steeper than for your fed batch setup. On the flip side, when you do go to a production environment, the scale up is generally nowhere near as high as what it would be for a fed batch. I think a lot of people are targeting 500 liters as their maximum production size for perfusion. And so in theory, you can make up some ground on the back end in terms of scale up hurdles, in terms of seed train development, because you're not going up to 15,000 liter vessels.
Jihong, what are some of the most common mistakes you see people make during the process of transitioning to using a perfusion workflow, and how can they be avoided?
I think some people do not take time to identify appropriate perfusion medium, or even though they found it, but they are unwilling to take a few weeks to adapt their cell clone to the selected perfusion media. I think the media is critical for a successful perfusion culture. Finding suitable perfusion medium and adapting the cells well in the new medium before performing perfusion culture are equally important. In addition, do not. In addition, some people push up the VCD with a high perfusion rate, but I think it's not economic and would increase the cost of manufacturing. Large amount media used also causes loading of the cell retention device and the downstream process, as well as the trouble for liquid handling.
It's absolutely accurate. Spending the time up front is key. Taking the time to make sure your adaptation is complete. And the additional point I think I would make in regard to your cell retention device would be understanding how much risk you're incurring with sizing your cell retention device, and making sure that if you are running close to risk in terms of sizing, that you do have integrated monitoring, as Jan has made mention of several times, so that you have that ability to swap to a new cell retention device, to a new filter, before it causes a problem for your process.
So, Jihong, as we come towards the end of our conversation, would you like to talk about any recent innovations or future developments on the horizon that can make this transition easier in the future?
Currently, the continuous process is a hot topic in the biomanufacturing field. For the continuous perfusion, tight control of various parameters to maintain the culture condition at the steady state is very important. This leads to many new inline measurement instruments are designed and launched on the market to facilitate the continuous monitoring of the critical parameters such as cell density, glucose, and the lactate concentrations. during the perfusion process. In addition, automated sampling devices are available now to avoid the possible contamination by frequent sampling. Some equipment supplier also launched the perfusion-specific bioreactor with integrated software and hardware, like cell retention device and the liquid transfer pumps, which also makes the setup of the perfusion process be more easier and friendly.
Vicky, what are your thoughts on the future of continuous perfusion processing?
I'm quite interested in the big data challenge right now, and I think the many software solutions that are on the market right now and are emerging are might be a big player in the future. Just so you can have many of your experiments run in silico instead of in vitro here, and get an idea from the mathematical modeling of the system what would happen in a bigger tank. So this is the one. So I've seen talks where people were modeling mathematically the distribution of oxygen in this dissolved oxygen in the bioreactor tanks, and I think that might help by adopting this technique for companies who are not doing it right now. And another thing is, which is also very forthcoming, I think, is the integration of the continuous downstream in this process here. Because we are talking about liquid handling, but if you're having a continuous downstream process just right after the upstream process, then it's not a big issue here.
Finally, Christopher, before we conclude the conversation, what are your thoughts?
On that part, that's kind of part of the joy of having perfusion, because you can get so much more benefit from automation and from some of the PAT that's been emerging, the process analytical technologies that's been emerging for better online at-line signal generation, for being able to better optimize your process and tune things. And with regard to downstream, where we're looking at pretty much all the major vendors are supporting multi-column downstream, which marries really nice to a continuous upstream process, and you get an immediate, relatively large savings in resin usage by being able to adopt that model. And then in regard to the advances in data informatics and data handling, in addition to in silico modeling, when you are able to achieve a steady state, your output and input can be really tuned more consistently, and you can better see and measure the influences of variance in the input versus the output. Whereas in a batch, of course, everything's constantly dynamic and shifting. And so a lot of times you're really not getting to see what an impact something has until you've completed your process. So there's a lot of fun things with respect to perfusion that are really nice advantages to have on the backside.
I think this is a perfect place to conclude this conversation, and I'd like to thank all of our guests for their participation and insight into this interesting topic. I'd also like to thank you, our listeners. If you would like to learn more about Thermo Fisher solutions for perfusion bioprocessing, please visit thermofisher.com/perfusion or reach out to a Thermo Fisher representative.